Hi, good afternoon, everyone. Before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, we would like you to introduce yourself, your name, designation, company, and the country you are based in. Okay, it's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. Great. And thanks for confirming. I would like to thank you all for registering and taking time out on a Sunday to learn about the best practices for pressure vessel design in accordance with ASME Section VIII, Division 1. My name is 𝐭𝐡𝐢𝐬 and I will be your introductory speaker for today. It's a pleasure to host this webinar for you. This is our 74th webinar in a series of technical webinars we are conducting. As a practice, we are conducting one webinar every month. Please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates. Today, we have an experienced panel of speakers. I am with my colleague, Mr. 𝐻𝐻𝐽, Managing Director, Principal Integrity and Safety Consultant, Mr. Anthony James William, who is the General Manager. Moving forward during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on the topic. You can type your queries in the question and answer window, and you will receive a reply in the question and answer window, or we will answer it live. We will try to answer questions as much as possible during this session. As we will have a detailed question and answer session after the completion of the topic, please accept our apologies if your question is not addressed due to the high volume of questions we usually receive. We have to be selective. Furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussion through question and answer. Before we begin, although most of us are in the comfort of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those who are around us. Since this is a quite technical subject, we will touch on key theoretical and practical aspects of best practices of pressure vessel design in accordance with ASME Section VIII, Division 1. In this limited 2 hours, we request you all follow along with us and keep asking questions to help us make this session as engaging as possible.
Assalamu alaikum and good day, everyone. Today's topic is related to pressure vessel design and ASME code. So we will be covering it is a fundamental definitions and awareness about the family of ASME VIII section standard, and we will be touching the basic elements, basic definitions, how the various ASME Section VIII, Division 1, Division 2, Division 3. These are 3 design codes, and they are supported by, let's say, ASME 9 for welding, ASME 5 for material, NDT, ASME 2 for materials. So we will be covering those aspects and design aspects, and then we will be sharing with you a small case study which is based on PWHT, like how it works while designing any pressure vessel. So it's people who are senior in experience or they know already about ASME VIII or pressure vessel design. It might be a lower side for them, but they can refresh their memory by attending this webinar. Pressure vessel side, we always touch about asset integrity. So design integrity is practically supported by pressure vessel design ASME VIII, and since asset integrity by definition, we always call it is a combination of design integrity, operational integrity, and technical integrity. Design integrity means assure design for a safe operations. Technical integrity means keep it in, and operational integrity means keep it running. So ASME VIII, Division 1, Division 2, or BSPD 5500 standards, these are the basic codes which are used for design and construction of pressure vessels. In a family point of view, ASME BPVC family, mainly related to pressure vessels, and base of the a boiler and pressure vessel code. Practically BP is a B for boiler, P for PV mean pressure vessel construction or code, you can call it. ASME BPVC boiler pressure vessel code family, and ASME is American Society of Mechanical Engineers, whereas boiler and pressure vessel code, ASME was founded in 1980, first performance test code in 1884, first code issued 1914 and published in 1915. Latest edition is 2021. Then edition revised every 2 years. And previous edition was 2019. So it is a big family. If you say ASME Section 8, Section 2, Section 3, Section 4, 5, 6, 7, 8. 8 is coming as Division 1, 2, and 3. Then ASME Section 9, ASME 10, 11, and 12. Then there is a supporting family for piping, which is 31.3, 31.1, 31.4, 31.8. And similarly, like these all codes, when you go there, for example, nuclear side is covered under Section 3, and heating boilers are covered under Section 4, whereas Section 5 is NDE, which is non-destructive examination, and 31.1, if you see, is a power piping. See, you might have heard about ASME stamped vessels, or there are workshops who are producing or manufacturing vessels as per ASME Section 8, Division 1, or applicable codes, and they apply various stamps, which these called ASME stamped vessel, and these workshops who are manufacturing these vessels, they are also qualified and authorized by the ASME authorized inspection agencies. ASME stamps, which is S is a steam boiler stamp, A is a assembly of boiler only, U is a pressure vessel, which is applicable on ASME Section 8, Division 1. Then U is pressure vessel, ASME Section 8, Division 2. Then pressure vessel, ASME Section 8, Division 3. Then PP is a power piping, R is for repair, and NB is for national board. Various stamps are there, which people may hear as they enter into the vessel industry. Design and construction code, piping point of view, 31.1 as I referred earlier, then ASME 31.3. There's also for pipeline 31.4, 31.8. Then these codes like ASME Section 1, Section 3, Section 4, and Section 8, Division 1, 2, 3. These are normally called as design and construction codes, whereas supporting codes are ASME Section 2, Section 5, Section 9. Then reference ASME standards are, which are like ASME B 36.1, 36.19, and ASME B 16.5 are basically flanges, and ASME B 16.9 for butt welded assemblies, and then ASME B 16.11 and others. Similarly, normal keywords which are used in the code, which is shall mean mandatory, may not, prohibition, may, can, recommendation or exemption from prohibition, then should be called recommendation, and guidelines which are coming from ASME Section 9 and Section 7. See, then latest code which is available is ASME 2021, and there are some key changes which took place from 2019, like location part UG was changed, and location UG 11 was changed, and location mandatory appendices, certain changes are made, and location point of view non-mandatory appendices, certain changes are made. So we don't need to go through this, but we will be like a presentation point of view. These are the detail what ASME is publishing at the time of changes when new edition is being issued. Now, if we go ASME Section 2, which is the first code, which is a supporting code basically. So it is a materials selection and material property code, where part A, part B, part C, and part D, where part A is a ferrous material, part B non-ferrous material, Then part C is welding consumables, and part D is the properties and stress values of the various materials. Then ASME material introduction point of view, ASME section 2, we are still there. It is classified material based on name and grade. Ferrous materials start with SA, non-ferrous materials start with SB, welding rods, electrodes, and filler material start with SFA. Part A, B, C, which provides information regarding ordering information, manufacturing processes, hot cold forming, normalizations, and others. Then chemical properties like carbon, manganese, sulfur, and other contents of the material. It's a steel material or non-steel materials both. Then mechanical properties like yield, tensile, elongations, hardness, and other properties. Supplementary requirements, which is lamination and impact tests. Common material forms point of view are shapes what we normally use. These are plates, structural profile, forgings, casting, pipe, welding materials, nuts, bolt, washers, rods, and bars. Like all materials which are used for manufacturing of pressure vessels or pressure containing components, there could be various shapes. So we should be familiar with those. Then every section 2, next is like types, for example, of the material point of view. Carbon steel is one type, low alloy steel, high alloy steel, then non-ferrous material, cladded materials. So carbon steel family point of view, the names which are common is SA 516 grade 70, 60. Then there's also SA 285 for piping. There's a SA 106 grade AB and SA 53. For flanges, SA 105. And for structural steel is SA 36. Low alloy steels like SA 387 grade 11. Then high alloy steels are SS, duplex, and other materials. So as a family point of view, if we try to see, like for a carbon steel family, there are various type of materials which are used for the pressure vessel components, like plates, pipes, forgings, fittings, and bolting. So in the same carbon steel family, we try to see plates, let's say 516 grade 70, 60, 65, or SA 515 or SA 455. So for that, pipe will be coming with a material SA 53 grade B or grade A, SA 106 grade A or grade B. Similarly, forging or the flanges part will be coming as SA 105 or SA 181. Then there is a fitting like SA 234, and bolting material goes by SA 193-B7 as well. So if you see that, like in the carbon steel itself, it is not the case like whole vessel would be made by 516 grade 70. So their nozzles will be made with SA 53 grade, SA 53 grade B or SA 106 grade B, and flanges of those basically nozzles would be made either SA 181 or SA 105. And our fittings, there could be a casting material could be SA 234. And the same is the case if we go by like chrome materials also, or SA materials as well. If you see here, stainless steel in the bottom side, SA 240-347, then the 312 is the pipe material, and SA 182 for SS material is the forging, and SA 403 is for the casting, and then the bolts wise also SA 193-B5. Under part D, where we get various properties, if you see stress, allowable stress values, yield stress values, and it provides values which we use for the thickness calculation formulas. And there are other appendices also which are mandatory appendices, and non-mandatory appendices are also available in the standard. Now, if we go to section 5, which is previously we covered was section 2, which talks about various material of constructions which are used for building or for making of pressure vessels. So these standards in simply are in a normal definition point of view provide data regarding the material of construction which is used for the construction or building of the pressure vessels. Now we are going to Section 5. Section 5 is basically a techniques, non-destructive examination techniques, which are used during fabrication or construction process of pressure vessels. And these techniques are covered in detail. So requirement for non-destructive examinations are covered under this standard. Then commonly known as NDT means non-destructive testing. Materials are tested without destruction or affecting its basically its shape or its properties. Then qualification of personnel, like people who would be doing NDT activity like ASNT level 1, level 2, level 3, or training requirement of technicians who will be doing the NDT activities. Then inspection and examinations, like how those NDT technique to be applied. So technique point of view, which are the common techniques, the most of you might be aware. One is radiographic testing. We are talking about techniques which are used under new constructions. Yeah, like when we are making pressure vessel, those techniques are used. So RT, UT, and then DPT, MPI, eddy current, visual examination, or leak testing or hydro testing. So here, when we say radiographic examination, is called normally RT. Ultrasonic examination is called UT. Ultrasonic examination method for materials, right? And the liquid penetration examination is called LPE or DPT. MPI or MPE, this is called magnetic particle examination. All these techniques are like they got certain advantages or disadvantages, but these techniques are covered under this code. Like common NDT methods, for example, the same detail we are adding a little more. For example, visual inspection by eye, magnetic particle examination by magnet, then film evaluation, which is RT, if you can shoot like just like X-ray of the body. Then DPT, dye penetrating inspection, is using basically a color and a solvent to develop it. And then UT thickness also applicable to see the quality of the weld or the material. See, if we try to see what are the uses and advantages and disadvantages of these techniques, like radiography, visual, liquid penetrant, magnetic particles, and ultrasonic. So here, defects detected, which is a gas, like, for example, if welding is done, so RT is done to see the quality of the weld. There could be inclusion, there could be incomplete penetration, crack, or slag. So it can see like by just like X-ray of the body, we can see the defect nature. So it's a permanent nature of record, and it can detect small or big flaws. Limitation point of view, it is basically costly, and it requires hardware and radiographic source. Then visual inspection, like, is a most effective technique, but it can look at the defects which can be seen by naked eye. It can see normally porosity, holes, slag, inclusions, and weld undercuts. So it's it's got limitation. Any defect below surface cannot be seen by naked eye. Similarly, DPT or liquid penetrating testing. So it is we apply a color and then a solvent to basically color it. It shows defects or cracks mainly on the seams or porosity. It can also tell you little pits or inclusion or shrinkage can be seen through this technique. So it can be applied both ferrous and non-ferrous material. Magnetic particle also is the second technique, but it is used only at the ferrous material, where you try to spray or put the iron particles, and then you bring the magnet, and it tells you the continuity or discontinuity of the surface. So ultrasonic is like a technique where we can use a reflection technique or refraction technique of the rays. It can be used to see the thicknesses and the lamination in the material. So next code is ASME 9. ASME 9 is basically welding, brazing, and fusion code, like for when all these plates or materials are welded together to make a pressure vessel. So ASME Section 9 provide all the guidelines to carry out welding activities or brazing activities or fusion activities, which are used for the building of the pressure vessels. So definition point of view, the code scope and definitions are represented by QG, these terminologies in the code. Then welding requirements represented by QW, brazing requirement by QB, and plastic fusion requirement by QF. Then by definition, the welding is a technique that joins metals by melting the base metal and causing fusion. Whereas brazing is the metal joining process which produces coalescence of materials by heating them to a suitable temperature and by using a filler metal having a liquid above 840 degrees Fahrenheit or 450 degrees Celsius and below the solidity of the base material. The filler metal is distributed between the closely fitted surfaces of the joint by capillary action. And whereas fusion is the coalescence of two plastic materials members by the combination of controlled heating and application of pressure approximately normal to the interface between them. So these are three techniques. In pressure vessel, normally we go by the welding, and more knowledge is required regarding welding. Under welding, so QW is covering the welding requirement, and this one is further subdivided. Like welding general requirements is a QW 100 to QW 190. Then welding procedure qualification covered under QW requirement point of view, QW 200 to QW 290. Then welding performance qualification is covered under QW 300 to QW 380. Welding data point of view, QW 300 to QW 380. Welding data further like QW 400 to QW 470. Standard welding procedure specifications, QW 500 to QW 540. When we say QW welding process qualifications or welding procedure specification is like a we normally use PQR, WPS. So when we say WPS mean welding procedure specification. So it is described the welding process used, the base materials used, then joint design, geometry of the joint, gases and flow rates, welding position, and include all the processes, conditions, and variables. So there is a form which is covered under form QW482 is suggested form for WPS, where details point of view the form the side is right side is also shown, but form can be seen in the standard which is QW482. It joint, base metal, filler material, position, PWHT, preheat, gas as per the type and electrical characteristics, weld pass, processes, filler metal, and techniques like a bead, back gauging, grinding, etc. are referred. So, in like a knowledge point of view, like you should know that like these techniques, these guidelines are available in the standard, and we don't need to remember by heart as such. Then PQR mean procedure qualification record. Here, like when a WPS is written, then it should be practically qualified and it's applied by a qualified welder. And then whatever preposition, whatever the filler material, the position of the weld, speed is applied, the weld quality is further checked if we got the homogeneous weld and it's meeting all the required specifications for the welding object. So the document that qualify the welding procedure specification that called procedure qualification record. And to qualify WPS, a procedure qualification plate is welded in accordance with the code requirement and actual test parameters are recorded. Then form QW483 is the suggested format for WPS to record PQR basically. Then like when these welding process is being applied or WPS is being applied, so it is being applied by welders, by people or by machine. So in that scenario, welder performance qualification is also a mandatory requirement, so as it can be ensured that both the technique as well as the welding process and welder they are intact and there would be no risk for the object, and we will be able to get the homogeneous welding quality. The document required by this code is like is called like a form QW484 is suggested format for recording WPQ. like a welder performance qualification requirements. Then if we go next, what are the type of the joints which are normally applied while making pressure vessel? One is the butt joint, and other one is the lap joint, then corner joint, T-joint, and edge joint. So all these welds got techniques are applicable at the given locations, and there are further like a qualification or criteria of calculation, like which joint should be applied where, and further guidelines are available in the ASME code. Like this is example of butt welds. Like here, if you see the first fabrication of the plate is like done, and they are placed in a position so the welding could be made. There should be proper alignment, proper dimension checks. It's called after fabrication, like a fit up. Once it's a fit up, then there are various weld areas. Like in the bottom, this is called like a root opening. For example, this arrow, root opening, and then root face. There is a penetration of the weld area point of view, face of the weld, size of the weld, effective throat. Then there is a face reinforcement which is comes on the top of the weld. Toe of the weld is here where the weld is on the corners. So root reinforcement. So there are various terminologies which are used while talking about the weld inspection, or while we talk about WPS qualification, RPQ, or records point of view. Here, common weld defects, like when it's not easy, like if anyone can come and make the pressure vessel. So it's a very sophisticated technology, and it's to be governed by properly qualified people, and job should be done by qualified welders. So if you see that if a non-qualified welder would be doing the job, then there could be basically issues, right? And there are various kind of defects which could be present in the welds of the pressure vessels. So one thing, gentlemen, and ladies who are attending the seminar or webinar, I would clarify that there would be a break in between where we will be answering the questions. Please keep sending your questions, and we will be answering in the middle after this theoretical part would be over. So we will be like attending all the questions almost. So here, if you see the type of defects, like between weld bead, for example, there are various weld beads, 1, 2, 3, 4, 5. So there could be defect in between the beads. Then there could be also between adjacent passes of the weld, there could be defect. Next is like a lack of fusion point of view, incomplete filling at root one side, right? Then incomplete filling at root. Okay, right. So if there's any, you can tell me. Fine. The incomplete filling at the root. The incomplete penetration, for example, if you're here in the bottom, there is an incomplete penetration here. And if you see this point, incomplete filling at root one side only, then incomplete filling at the root means the lower part is left empty. So there could be various kind of defects. At least there are 9 kind of defects in the normal butt weld, which could be reported by RT. Then, like we are going to the another standard after ASME 9, which was basically, if I go back, it is talking about like welding processes and WPS, PQR, and then what kind of defects are there, then the type of common like joint types and various forms, right? This we covered, and these are available in ASME Section 9. Now, there are the flanges which are connected with the nozzles of the pipes, nozzles of the pressure vessel, and all the flange connections are governed by ASME B16.5, which is called pipe flanges and flange fittings. So this is the standard, if you see that, and it covers basically like a flange diameter 1.5 to NP24. So used to connect pipes and its components like valve, strainer, others, identifies acceptable pressure temperature combinations. There are 7 classes in basically pressure vessels, which is 150, 300, 400, 600, 900, and 1500 and 2500 ratings, we call it. Then flange strength increase with the class number, material and design temperature combination without pressure indicated not acceptable generally. So if we see a vertical pressure vessel, so here you can see a flange connection, another flange like a nozzle and a flange at the end. This is like you can see here. And we'll be coming various components of the vessel in the coming slides also, but like in a pressure vessel, top side is called head, then shell, bottom head, and these are the supporting legs. So, here, if you see facing type generally for the flanges, flat face, there is a raised face, and RTJ ring type joints basically. Then standards which is covering up to 1.5 to 24-inch dia flanges is covered under ASME B 16.5, whereas 26-inch to 60-inch flanges are covered under ASME B 16.47 standard. Then type of the flanges also based on the neck and there are two type areas where you can define the flange. One is the neck side, one is the face side. So here, this is called neck. Weld neck mean here this part of the flange would be welded with the pipe. Then slip on mean it could be like a slip on the pipe itself. Then socket weld flanges are also there. Then threaded flanges are there. Then lap joint flanges are there, right? And then reducing diameter flanges are also there. And then blind flange without hole. Then orifice flange. So various kind of flange are there which are used for pressure vessels or for connection of the pipes. Here, general material groups for the forging material, casting materials, and plates, general, and combination point of view did cover earlier. But here, for example, if we have a carbon steel, normal definition, then casting material would be SA216WCC. Similarly, if you take 1.1 carbon steel and a normal carbon steel like a plate, then forging would be A105, casting would be under 216WCB, and plates would be covered under ASME A515 or 516 grade 70. This is a combination. We covered this earlier also, but here we are just reflecting again. In a construction of pressure vessels, the combination of various kind of materials would be required because everything is not made on similar kind of carbon steel material or SS material. So this is one of the rating point of view. So we have like a grade 1.1 is a flanges, then grade 1.2 flanges, grade 1.3 flanges, right? Under this, the rating is given 150, 300, 400, or 150, 300, 400, 150, 300, 400, and then as temperature is increasing, the pressure bearing capacity of these flanges would decrease. Between -20 to 100 degree Fahrenheit, like a 150 rating flange can bear up to 285 psig pressure, and 301 can bear up to 740 psig pressure, and 400 can bear up to 990. But same flanges, if temperature goes up to 1000 degree Fahrenheit, the pressure bearing capacity of 150 rating flange is only 20 psig, 300 rating is 50 psig, and 400 is 70. So this is a range when we need to apply a flange at any design to a pressure vessel. So we have to keep in mind what kind of flange we need to apply there. That will depend on the applicable pressure and temperature rating and their combination. So here, if we see like a various kind of pressure vessels are there, or how the pressure vessels are used. So here you can see a horizontal pressure vessel. It could be a separator, it could be a knockout drum, or it could be just a horizontal pressure vessel. And there's a vertical column, distillation column, reactor. So this could be another example. So there could be heat exchanger also, which are part of the pressure vessel as well. So we use pressure vessel in various kind of industry, which is petrochemical, upstream, downstream, refineries, then chemical plants, power plants, pulp and papers, food industry, pharmaceutical industry. So pressure vessels are used at wide spread. Then here, like a pressure vessel in horizontal form, vertical form, or it could be spherical form as well. So third example is a spherical pressure vessel. These type of vessels are made based on the process requirement of that particular industry. Like the spherical vessels are used normally to store LPG. And these are the normally called vertical vessel or horizontal vessel as a process vessels. So in a normal, like a type point of it was previous slide also. So there's a shell, head, nozzle, and support. The shell mean here, and nozzles are which are flange nozzles, and this is a saddle support, which is at the bottom side of a horizontal vessel. So just to get familiar, the people who are new to the pressure vessels. Then shell, it is the primary component that contain the pressure vessel. Then a pressure vessel shell in the form of different plates are welded together to form a structure that has a common rotational axis. Then shell are either cylindrical, spherical, or conical in shape generally. Then their heads, for example, when the vessel end type is closed, so the vessel could be elliptical side, hemispherical, toruspherical, conical, flat head, or bolted head. Bolt is not shown, but these three are shown here. The nozzles, like when a pressure vessel is connected with incoming pipes, outgoing pipes, so you need to have those connections, and that's called basically nozzle. A nozzle is a cylindrical component that penetrates into the shell of the pressure vessel or head of the pressure vessel to make entry of the fluid or take exit of the fluid from the pressure vessel. They are used for the following application: attaching piping for flow into or out of the vessel, attach instrument connections, level gauges, thermo valves or pressure gauges, then provide access to the vessel interior at manway. Like manways are also a form of the nozzle, provide for direct attachment of other equipment items. For example, heat exchanger could be connected direct to the pressure vessel as well. Supports like a vessel has to be supported vertically or horizontally wherever, and these supports are also welded with the pressure vessel. Support is used to bear all the load of pressure vessel, earthquake and wind loads. There are different types of support which are used depending on the size and orientation of the pressure vessels. It is considered to be the non-pressurized part of the pressure vessel. Then like a saddle support is like a horizontal vessel. There's a bottom of these plates, which you can see here. They're called basically saddle supports. So when we're applying these supports, so one side of the support is normally fixed, other one is sliding. So a thermal expansion of the pressure vessel, horizontal pressure vessel could be accommodated. So again, the component is coming again, horizontal pressure vessel also like a vertical pressure vessel. So this saddle support comes at the bottom, other are the shell, nozzle or head. And the section wise, if you see a pressure vessel on one side, it looks like this. Leg supports, like some pressure vessels are supported by, there are various kinds of supports: leg, lug, skirt. So there are three main names which you use for the basically supporting the pressure vessels. So leg mean these are the legs that you can see on the side, and the spherical vessels are spheres are supported also by the legs. So small vertical drum are typically supported on leg that are welded to the lower portion of the shell. Reinforcement pads are welded to the shell first to provide additional local reinforcement and load distribution. Support legs are also used for spherical pressurized storage vessels. So this is a vessel. A vessel is supported on a vessel as on a platform intermediately. These kind of supports are called lug supports. Then the example as a vertical reactor, for example. So what could be the new in the vertical reactor? There could be a catalyst bed, or there could be a like catalyst bed support, lower catalyst bed, and then there could be lowest bed, catalyst bed support also. Then head, inlet nozzle, outlet nozzles, and outlet collector or a shell. So if you see this if we change pressure vessel to a reactor form, so in a reactor form, there would be only changes in the internals. Outside, it will remain just like a pressure vessel. So there would be additional fittings which will be made inside the pressure vessel, or there should be a catalyst, and there could be a various distribution equipment which are installed inside the reactor. So skirt support, for example, like a vessel is supported in the bottom. If you see this vertical vessel, and this part is called skirt support. And if we make it a model in PV Elite, so this is this conical part is called bottom skirt. And there could be a top skirt also if it's made in two parts, like a vessel starting here in the head onward, and the bottom part, this called skirt. And skirt is a non-pressure bearing component, and it is made to support the pressure vessel on the basically location where it is installed. Then vessel design is support, like how we design this pressure vessel supports. So there is an equation, normally we call it for horizontal vessels, LP-Zick method. Commonly governing the stresses in the saddle support are bending stresses, tangential stresses, circumferential stresses, horn of saddle, and bottom of the shell. The supports are designed on wind and seismic codes. Commonly used wind code is ASCE, and commonly used seismic code is UBC, which is called building code normally. And then skirt support according to different books like Brownell and Young and like Bednar. These are the basically handbooks which are also available to design the vessel skirt supports. So here, ASME section, like further is like it provides when we say normal, like what it does. When we say ASME section introduction point of view, if we go on the design part, like what we have been flowing by now, we started with like what are the supporting codes, like ASME section 2, then ND, like first one was the material, then second one was the NDE, third one the ASME 9 for the welding, then we went to the supporting standard like ASME 16.5, and then how the supports are designed, which are non-pressure containing part. Then we come to the pressure containing part. So it would provide basically ASME 8 section 8, ASME section 8, which I should say, if it provides requirement applicable to the design, fabrication, inspection, testing, and certification of pressure vessels operating at either internal or external pressure. This code was established 1925, Section 8, Division 1. Like ASME Section 8, Division 1, operating pressure like is range 15 psig to 3000 psig. It works with safety factor of 3.5. Before year 2000, this safety factor was 4, and it is reduced to 3.5 during the year 2000. It works normally under the membrane stress formulas, both longitudinal and circumferential stresses. Whereas ASME 8 Division 2, its operating value goes from 3000 psig to 10,000 psig, and the safety factor is reduced in the case of because thicknesses are too high, but more stringent finite element analysis or fatigue analysis requirements are added. More stringent welding control and material control activities are applicable under ASME 8 Division 2, where safety factor is reduced to 2.4. There is also for very high pressure vessel, the safety factor is even less than or equal to 2.4, and the guidelines are provided under ASME 8 Division 3. Normally in oil and gas industry, we remain between like ASME Section 8 Division 1 and Division 2. I have never come across with Division 3 for pressure vessel. So now here, like various like codes by U1, U2, U3, U4, and U5, like scope, general, standard reference by this division, units of measurement, tolerances, then section. Like this is how the code is organized. The information point of view, index point of view, when we say anything under UG mean, it will be providing design guidelines with reference to materials, design itself, fabrication, general requirement. It's UG mean general requirement with reference to inspection, marking, and over pressure protection. Then subsections, for example, UW mean welding welded pressure vessels. UF mean forged pressure vessels, if there are any. Then UB mean brazed pressure vessels. Then some sections like C, material point of view, UCS is carbon and low alloy steels, UNF is non-ferrous material, then high alloy steel and so on. So like what kind of material is being used for the pressure vessel when we go to design side, so we can go to the relevant side of those sections. For example, if it is a low temperature service of a pressure vessel, then ULT, low temperature service, can be applied. Similarly, cladding and lining aspects are covered under UCL. Next, like a general aspect point of view, if we say material, UG4 through UG15 materials are covered. Design formulas are provided for the pressure vessel hoop stress formulas under UG16 to UG35. Nozzle designing, reinforcement of the nozzles are described and covered under the standard clauses of UG36 through UG46. Then brazed and straight surfaces, UG47 through UG50. Then fabrication aspects are covered under UG75 through the UG85. Inspection and tests are covered under UG90 through UG103. Marking and reports are UG115 through to UG120. Overpressure protection UG125 through UG140. Then requirement for pressure vessel fabricated by welding, like a UW through like a general UW part, like a first part we're covering as UG part, no general requirement. Now UW requirement, welding point of view, general through UW3, then material UW5, design UW8 through UW21, fabrication UW26 through UW42 and so on. Then UCS, requirement for pressure vessel constructed of carbon and low alloy steels. So UCS 1 general, materials UCS 5 through UCS 12. Here UCS 66 is more common at low temperature. That is like MDMT, HRP testing. So that is like a UCS 66 is more common, like a standard clause, which I think mostly pressure vessel designers are familiar, and they need to keep that also for the production of fatigue failure of the brittle fracture failure of the pressure vessels. Then fabrication of UCS 75 through to UCS 85, like mostly pressure vessels are fabricated or they're made of carbon steel and low alloy steels. So these clauses are more relevant to us in normal day-to-day use. Then when we're making a pressure vessel, if it's a horizontal, like is a reboiler, so it gives you a good example like how it would be welded, like what kind of welds would be applicable. So here the type of welds which are like a butt joint, a straight one, A type, then B type here, D type, B type. So various type of welds are there, and these welds are configured like for the welding design and the quality control point of view. Like here, if you see acceptable joint categories A, B, C, D, and here the various, like based on the what kind of radiography or how much radiography would be done. So full radiographic efficiency could be 1, support it could be 0.85, and no radiography, then we have to take the basically joint efficiency up to 0.7. That is a further calculation when we're calculating into the hoop stress formulas. So these aspects we need to remember: acceptable joint categories and degree of radiographic examination. And this is weld joint efficiency, which are covered under UW12. Here, like the requirement of the RT testing of these welds are covered under UW51, full RT, and UW52 spot RT for the inspection of welded joints. So here RT1 full, RT2 maybe 10%, RT3 spot, RT4 other spot, and it can be applied based on the choices, and details are given, and then accordingly under RT1, RT2 joint efficiency is 1, here is 0.85 is the joint efficiency. Loadings like is also important part, UG22, like what are the basically loads or pressures which are applicable on the vessel while designing it. So there could be a pressure requirement, internal pressure, external pressure. Then there are dead loads of the fluid itself or platform which are being supported by the pressure vessel. Then pressure vessel might be designed under cyclic service. Under the cyclic service, cyclic load has to be taken. If there could be a wind load, there could be a seismic earthquake loads, and there could be a piping which are connected. So their loads might also be coming on the nozzles of the pressure vessel. So we need to consider all applicable loads while designing pressure vessel itself, its support, its nozzles. Now, minimum thickness requirement, for example, under UG 16, like a minimum, like for general service, like any pressure vessel, the thickness should not be less than 1.5 mm. For air or water service, as well as steam, air or water service, the minimum thickness of any pressure vessel, irrespective of diameter, should not be less than 2.5 mm. Similarly, unfired steam boilers, the minimum thickness is referred as 6 mm in UG 16 of the standard. Then these are just a formula, hoop stress formulas for circumferential stresses and for longitudinal stresses. So if you see this longitudinal stresses point of view, the thickness required is half of the circumferential. So circumferential stresses are almost double of the longitudinal stresses, where E is joint efficiency, P is internal design pressure, R is inside radius, S maximum allowable stress value, then T is the minimum required thickness of the shell. Similarly, for the elliptical heads, similar formulas are there, little modification, and hemispherical heads as well. For flat head design, for internal pressure, the formula is D is equal to D Cp over SC, which is covered under UG 34, whereas UG 32 is for the elliptical or hemispherical heads. Then shell design for external pressure is also important, and here D naught to T value, if it is greater than or equal to 10, calculate L over D naught first, then calculate factor A for figure G of ASME section 2 part D, calculate factor B, and calculate PA. Then accordingly, the rafters and external thickness aspects are being basically calculated. These are the external, like ring or rafters, which are applied to basically protect the vessel against external pressures. And mostly, like these rafters or the movement axes of ring are welded outside, not inside. Then design of the pressure vessel nozzles or nozzle opening or reinforcement. So these are, first we said like UG 37 to onward, those are covered by the design guidelines. Then the pipe, which is covered for the nozzle of the shell, nozzle like a cylinder, is ASME B 36.10. And then flanges, which are covered under ASME B 16.5. Then reinforcement pads are designed as per the code. The type of the opening could be process nozzle connection or inspection opening also. Process side, which are connected with the pipes or instruments, inspection openings could be the manways. See, these nozzles can be connected pipe like a welded to the shell, then pipe is connected with the flange and reinforcement pad, and it's connected with the incoming piping or instruments. Then forged vessel connections, self-reinforcement nozzles are also there, lip type nozzles are there, pad type nozzles are there. Nozzle of 2-inch and smaller do not require reinforcement under Division 1 for all vessels. Nozzle 3-inch and smaller do not require reinforcement under Division 1 for pressure vessels with wall thicknesses less than 10 mm. UG 36 to UG 46 are helpful for calculation of the reinforcement of the nozzles. Also, Appendix 1 to 7, Appendix 1.7 and Appendix 1.10 are also guidelines for the nozzle design and reinforcement. Limitation point of view, like what would be the maximum nozzle diameter? see, for a vessel where diameter is like 1.5 meter or 1500 mm, the nozzle dia, half of the vessel dia, but not more than 500 mm. It is not the case like we can make any size of the nozzle on a small dia vessel. If the diameter of the vessel is greater than 1500 mm, then it can be up to 1/3 of the vessel diameter, but not more than 1000 mm. Exceeding these limit, additional requirement of Appendix 1.7 shall be applicable. Nozzle may also be designed with alternative rules of Appendix 1.10 pressure design. These are applicable as well. So here, if you see the nozzle on a pressure vessel, so it is showing various kind of connections, like it is shown, like it's not a practical, but it is shown like there could be a reinforcement pad, the base metal, then the nozzle itself, and welding, fillet welding, butt welding. Those aspects are shown in this drawing. And here, internal diameter, external diameter, then the various dimensions what you mark on the drawing, base metal itself, reinforcement, or the edges also shown here. Then additional reinforcement, for example, reinforcement pad, necessary if insufficient excess thickness, must be located within the reinforcement zone. Allowable stress of reinforcement pad should be same that of shell or the head. Additional reinforcement sources like pad, it could be, or it could be also like additional thickness is shell or lower part of the nozzle could be integrated part as well. Then, like design of the nozzle opening and reinforcement, the method used by UG 37 and Appendix 1.7 for reinforcement of the nozzles. The simplified ASME rule, area replacement, metal used to replace that if removed should be basically compensated, must be equivalent to the metal basically area which is removed by the nozzle, if same can be provided by the reinforcement pad. Must be adjacent to the opening. Limit of reinforcement are basically defined under UG 40. So here, if you see various nozzle designs are there, like full penetration weld with integral reinforcement, like here. Then separate reinforcement plate could also be provided outside here or here. Similarly, full penetration weld, here if you can see, to which reinforcement plates may be added. So here, like various type of welds are types are there when applying the nozzle, but there are standard nozzles design which are guided in ASME basically. Type of the then next part, once the nozzles are made, flanges are attached. Then these flanges are to be connected with the incoming flanges of the pipes. So for those flange to flange connections, we need to add gaskets, and there are various kind of gaskets as a specification point of view. We need to know and we need to use them. There's like a compressed fiber sheet, spiral wound type of a gasket is there, ring gasket, oval or octagonal type. Then ASME B16.20 dimension for spiral wound or ring type gaskets for standard flanges according to the ratings. Then ASME B16.21 dimensions for compressed fiber gaskets for standard flanges according to the rating to be used. Then, like one aspect here where I touched this subject further also, previously also, UCS 66 is very important clause of the ASME Division 1, which protect vessel against brittle fracture. Brittle fracture is a very likely threat for the pressure vessels. For example, if a pressure vessel is, everybody is aware pressure vessel design at the for the high temperature service, but sometimes there could be low temperature in service. For example, if a nitrogen vessel, if it is a filling, like providing nitrogen for the purging of the plant and nitrogen being filled in the same vessel. So what may happen, like once we will be releasing nitrogen for purging, there would be a drop of temperature in that particular vessel. And at the same time, if new nitrogen would be filled in that vessel, and then it means stresses would be applied. And due to low temperature, there could be a lack of toughness in that material, and there could be a failure in the pressure vessel. Practically, one failure occurred a few years ago, which we did in the RCA. So the cause was basically simultaneous releasing of nitrogen and then filling of the nitrogen, and that caused the failure of the pressure vessel. So brittle fracture and MDMT mean minimum design metal temperature, and Charpy test or impact test. These are the very commonly used words in the welding qualification, WPS qualification of the pressure vessels. So MDMT is a minimum design metal temperature, minimum expected temperature while operation of the pressure vessel, minimum. High temperature we always take care. So we have to take care of the low temperature as well. Failure due to brittle fracture means if toughness of the material is lost due to low temperature, and if load is applied on the same time, then vessel may fail. See, impact test exemption or requirement as per ASME Section VIII, Division 1, where UCS 66 curve is important here. If we see here, thickness point of view, just a minute. So here, basically, if we see the curve, minimum metal temperature and the thickness point of view, and whatever the curve is applicable, we can see that, right? And here, basically, right? So these curves we need to follow while looking at the whether MDMT point of view, what kind of test normalization required or impact test could be exempted or not. Then one other aspect, like after UCS 66, PWHT or post-weld heat treatment is also important activity, and this activity applicable on certain thicknesses or the basically lethal service of the vessel, and PWHT done to pessimate or to minimize the stresses or residual stresses in the weldments which could be caused by the weldment activity. The post-weld heat treatment is the process in which the stresses from the material are removed. Requirement of PWHT as per ASME Section VIII, Division 1, UCS 56 for carbon steel material should be referred. Stress relieving is the process in which the stresses after cold forming are removed. The forming strains due to extreme fiber elongation could be caused. Now, like a post-weld heat treatment point of view or stress relieving point of view, when required as per UW2, UW40 and specification, PWHT must be performed according to UCS 56 and table UCS 56 as well. Review PWHT specification for specified thickness and material and verify PWHT graph as per UCS applicable standard requirements. So PWHT, UCS 66, these are the two requirements which are applicable based on the thickness and nature of the service of pressure vessel. Hydro testing, like once vessel is fabricated and then ready to go for installation, hydro testing is done. Before that, like we covered, like under welding, under fabrication stage, various kind of entity tests are done. Then under welding qualification, UCS 66, Charpy test or welding qualification test, some mechanical tests, tensile stress tests. Those tests are conducted. If due to thickness some PWHT is required to be done, then that is covered under UCS 56. And hydro testing is the last activity when vessel is ready to go. So here it's a non-destructive test part, and normally the hydro test pressure, which is water-filled vessel, test 1.3 of MAWP into a lowest stress ratio. Like lowest stress ratio means stress at water test temperature and then the maximum design temperature of the pressure vessel. That ratio is called, like lowest stress ratio means allowable stress at test temperature and allowable stress at design temperature. MAWP, maximum allowable working pressure at hot conditions. MAP is maximum allowable pressure at cold conditions. Water temperature shall be 17 degrees Celsius or above, rated MDMT to avoid brittle fracture during hydro test. And there are also certain requirements, like water should be drained and the vessel should be dried, so as no like a post hydro test effects are caused by the water if it is left inside the vessel. Vessel shall be tested after completion of all fabrication and examinations, like a UG 99, which is standard requirement, or like a UG 99 A1 and A2 requirement. Cosmetic and grinding on the base metal is allowed after this test. No other modification is basically allowed. Test pressure is already we qualified that. Then there is also one test if the vessel cannot be tested by pressure testing, hydro testing, then it can be tested by pneumatic testing. Pneumatic testing by using air or nitrogen. It is a more like a complicated and dangerous activity because explosion may take place during pneumatic testing. So under pneumatic test, vessels are kept in a guarded and safe location, so as it's not exposed to human if any explosion may take place. So this test can be performed instead of hydrostatic test if the hydrostatic test is impractical. Pneumatic test pressure is 1.1 of MAWP plus multiplied by lowest stress ratios. Pneumatic test is dangerous for high pressure due to compressibility of air, which may cause explosion at some stage. Then vessel marking and use stamping, which is normally last activity, like if the vessel marking should be done as per UG 1116, certification and authorization inspection mark is UG 1117, and marking method is given under UG 118. So these all guidelines are provided, and if like we try to follow as we code, it is a well-defined code and it can be used easily by the parties with certain guideline, certain supervision, but it's not a so difficult activity. Then steps were like a normal for pressure vessel design, scope defined by the client in RFQ. RFQ contain data sheet, sketch with nozzle orientation, pressure vessel specification. These are provided by the process design or a part of P&ID or equipment layout drawing. So mechanical designs are somehow blessed because they will be getting complete orientation, complete size of the nozzle and vessel, and mechanical engineers are required to design a pressure vessel only as per ASME 8, Division 1, Division 2, or Division 3, or as per BSPD 5500. Then calculation performed as per code specification and design basis. General arrangement drawings are prepared. Fabrication drawing for pressure vessel manufacturers are also prepared. And then like other than ASME 8, there is also BSPD 5500. It is a British standard, is also used in certain areas. Then BSEN 13445 is unfired pressure vessel design code. So these are also used in certain European Union countries. So before I go to the case study, there are some questions we can answer, Mr. Kale.
Yes, sir. Here, a question here. Is there any guidelines? Is there any guidelines are there for consideration of slope in designing a horizontal vessel, 1:100 or 1:500?
See, these slope requirements are like normally, see, you don't know whether the draw of nozzle is at what location. So these slopes are provided based on the process requirement and the nozzle location, so as the vessel can be emptied in the case of drainage. So thumb rule is what you indicated, but it depends upon the length and diameter of the vessel and the nozzle location for the draw.
Next question. Can you tell me that is it relevant only for mechanical engineering students or for any other type of engineers?
See, pressure vessel design, like mainly handled by mechanical engineer, but I'm a chemical engineer, so I've been also doing design of pressure vessels. So like chemical or mechanical engineers can do the pressure vessel design, but it will be like a distance away from the electrical support design. They are more relevant.
Next question. What ASTM standards for these welding joints and piping design?
See, ASTM I have renamed ASME. Before like 20-25 or 30 years ago, ASME B31.5 could be called as ASTM 16.5. So these are same, like ASTM is a different organization as compared to ASME, but pressure vessel related all designing aspects are covered under ASME, and ASTM is not applicable nowadays. Before that, like 20-30 years ago, ASTM had a more say in ASME, but not now.
Next question. What are the selection criteria for welding methods? When to use each type?
See, there is a code requirement under UG 12. All the welding requirements are defined, and then when coupled with ASME 9, so it's with the experts' decision, and there is also industry practice like what kind of weld is applied on what component of the pressure vessel, like nozzles, different aspect of welding applicable, and for shell joints, main joints, A type or B type, different kind of weld application is there. The application, like a diagram what I showed, the same diagram is available in ASME 8, like a UG 12, where these guidelines are provided. And of course, you need also experts or trained people to define these welding requirements.
Next question. I had a practical case study for SLCR ammonia tank. The designer called it open pressure vessel. Is it possible? Please clarify.
See, pressure vessel definition is like it should have a pressure between 15 psig to 3000 psig. If it's open pressure vessel, it means it's not a pressure vessel. And if it's open like a tank or open like a pot, then different design aspects or different design formulas would be applicable. It will not be considered as a pressure vessel.
Next question. Which type of welding is preferred for pressure vessels?
See, all the type of welding which we just covered previously, it's mainly steel pressure vessels. And if I go back, see, these are the basically various design on the welding point of view. Welding is by like when we go back, just a minute. So these are the weld joint types, UW, which is covering under the like what kind of weld types are applicable. So here is shown on the nozzle D type and so, and A type. And similarly, it would be covered under normal steel welding or UCS code. So that is applicable area.
Next question. Sir, could you please explain the difference between ASME Section VIII, Division 1, 2, and 3?
See, basically, these three standards, only difference is pressure range. Like Division 1 is applicable from 15 to 3000 psig, and Division 2 is applicable from 3000 to 10,000 psig pressure range, and Division 3 is applicable above 10,000 psig pressure. So that is the difference of the range of the pressure. And similarly, there is a compromise on the safety factor. For first Division 1, safety factor is 3.5. For Division 2, the safety factor is 2.4. And similarly, for 3 also, safety factor is below 2.4. So, but someone can say that, like, why there's a lesser safety factor for the high pressure vessels? The point is thickness is too big to accommodate that. And secondly, additional checks, additional fatigue, additional material quality requirements are added for Division 2 and Division 3 pressure vessels.
Next question. Can we do PQR without having WPQ?
See, there is a steps. First WPS, then PQR. It cannot be before.
Next question. If the design pressure is below 15 psig, can users still select ASME Section 8 for the
there's a, if you go by API 5, API 650 tanks, which are 2 to 3 psig is design pressure. So, and then there is a ASME API 620, which is pressure range is up to 15 psig. So other codes and specifications are applicable, which can be used at the low pressure vessels.
Next question. I'm a fresh graduate in mechanical engineering. Can you suggest a simple roadmap for those who plan to pursue a career in asset integrity or reliability engineering? Do you recommend exposure in the field during the first few years?
See, there are various business lines are available. For example, if you are associating yourself with a fabrication shop, which is designing pressure vessel or tanks for heat exchangers, so you can go into the designing field of these equipment. If you are joining, let's say, any company like us who is doing RBI or fitness for service calculations, so you can also associate with those. If you are working in any operating plant, you might be involved with the inspection activities. So then you will be equipped yourself with API 570, API 510 or APA 653 standards. So it goes like what kind of business line or job career you adopt, you get a chance. So, and it is not, there's no like a single thumb rule, but wherever you get opportunity or what your preference is, then accordingly you have to train yourself and you have to equip yourself with the latest knowledge and technology.
Next question. Are 400-pound flanges usually used, especially on pressure vessels?
Generally, no. Generally, I would say, yes, there are like flanges rating point of view, 150, 300, 600 also less, 900, then 1500 and 2500. But it is a part of the standard, that's why we mentioned. So there's also a question, fillet weld. Fillet weld is also used on the flanges, on the reinforcement pads for the reinforcement, like when we are applying the reinforcement pads and there's a fillet weld between two laps basically. So fillet weld is also applicable in the pressure vessel along with the butt welds.
Next question. Are swivel flanges used on pressure vessels?
See, pressure vessels, normally they are fixed flanges, but there might be a scenario where these kind of vessels these flanges are used. I'm not so familiar with those.
Next question. Please explain about welding of SS to CS material and joining of SS flange to CS flange as well.
See, these like when we are welding to dissimilar metals, so there should be a specific rules of the business which are applied. Otherwise, this kind of like joints are called critical joints, and the special welding procedure are to be developed when we have this kind of scenario. It is not so common to join carbon steel with SS.
Next question. What are the pros and cons of different types of flanges? Can you please give some examples?
So see, for various flanges are used at the various pressure conditions. Low pressure vessel, you will go by the 150 rating. For high pressure vessel, you may go up to 200 to 2500 pressure rating. And then their faces point of view, low pressure flanges are used, could be a flat face, whereas the high pressure vessels, flat face may not be able to prevent leakage. So you may need to go raised face or joint ring type flanges, so as there's a tight connection and the leakage chances of fluid outside the flange connection is not possible. So pro and cons is not a case, but it's a cost and pressure rating. And the selection and application is based on the pressure and temperature ratios.
Next question. What are the most in-demand certification skills tools in asset integrity?
See, under asset integrity is basically, if you remember my first thing, asset integrity, there are three elements: design integrity, operational integrity, and technical integrity. So in whatever area you would be working, so you need to equip yourself with those particular aspects of asset integrity. In design aspect, there is different skill level required. Under technical or under like a plant inspection and maintenance and operation, a different kind of skill set is required. And under operation point of view, if you are working, that is like more towards the operational point of view. And in those scenarios, you have to be equipped yourself, like how to manage various scenarios or let's say emergency response plans and how to react in terms of if there's any scenario at the plant you need to handle. So you have to see that as a young engineer, which area you get a chance to join, and then accordingly you can equip yourself. After engineering degree, all options are available for young engineers, and wherever you go and you try to excel your skills, you can do best and you can be a star there. So there's no need to be worried what should be your selection, but the important thing is what kind of organization you join and what kind of role is given to you to play.
Next question. Can vessels be made of composite materials such as carbon or glass fiber composite?
Those are being made and mechanism is different for those vessels. Yes.
Next question. If we clean a pressure vessel with steam, can the design temperature and or pressure be exceeded?
No, the steam out temperatures are always defined, and steam out or cleaning of the pressure vessel is always a normal practice during the shutdown of the basically facilities.
Next question. How can we choose destructive testing for a PQR?
see, during PQR, whatever destructive, see the question again.
How can we choose destructive testing for a PQR?
See, normally, CHRP test is being done. Number two, the tensile stress values are being checked. So these tests are already defined under ASME 9 and they are applied accordingly.
Next question. What is the difference between fired and non-fired pressure vessels?
See, non-fired means there is no fire in and around that pressure vessel, and fired means boiler or a heater. In those areas would be called as a fired equipment.
Next question. Under asset integrity, only static equipments comes or other equipments like rotary electrical.
See, asset integrity means asset covers all aspects and all type of assets and engineering disciplines, whether it's electrical, instrumentation, whether civil, structural, or mechanical, static or rotary. So each type of asset or each asset is required to be managed as per the applicable code and performance standards, and asset integrity is applicable on all type of assets.
Next question. What is the criteria of selecting head type of pressure vessels?
So it goes by the process type normally, and then process type is the main criteria, and see like what kind of process conditions are there, then what kind of head should be there for pressure vessel.
We can do last question for proceeding.
Okay.
The material designation mentioned earlier, such as SA105N, I noticed that they share the same designation numbers, like example 105N, with the ASTM materials used with piping standards.
See, previously SA 105 was previously noted as ASTM 105. Around 25-30 years ago, they started using term SA. They are no more using term ASTM, where N stands for normalized conditions. So ASME and SA, so I'm not so familiar with, both are the American institutions, and there is some collaboration and some distance also. Okay, sir. So I go to last part of the presentation, which is like a case study where design of a packed stabilized column will be. I will be showing you the what calculation we made, and it could be best if the time is there, but we are using limited time in these basically webinars. So we cannot go through the all aspects because only 2 hours are there. So I will be only showing the steps and the calculation modules of the PWHT software. And it is not so difficult as I learned many years ago when I was basically a chemical engineer, and I was given some supervision, some guideline by my senior mechanical engineer, and I was able to design. And at that stage, I was also promoted to the head of design section of that particular company. And being chemical engineer, I was heading the mechanical department also. So it's not so difficult, gentlemen, but we have to see what are the normal steps. And once you will be given any task, you will be able to design pressure vessel via manual calculation as well as via any software, whether I'm not recommending, but what we have been using is a PWHT, or there's also compressed software, or there could be other software as well, and you can use also spreadsheet for designing of pressure vessels. So here, since when we design any pressure vessel, so we get a complete detail from the basically user or the process side, who need this pressure vessel for their process reasons. So there would be a data sheet which will be giving a diameter, the material of construction, the nozzle sizes, nozzle orientations, the type of the support. So as a mechanical engineer, we need to just design that pressure vessel by applying applicable mechanical calculations. So in data sheet, normally we get diameter, length, volume, process data, design data, operating data, fluid, service, material of construction, and nozzles orientation, as well as the nozzles data, diameter ratings. Similarly, it carries that design code, sketch of the nozzle orientation, platform, and structures associated with that particular vessel, insulation, site parameters, wind data, seismic data, which are applicable on those conditions in that particular area, or weather data also. This is the vessel. If you see that this is the skirt in the bottom, right? And this is nozzle orientation, and all the nozzles like N6, N2, N1. These are all nozzles. They're like inlet outlet conditions, along with the rating and the weld neck raised face, weld neck raised face. So the type of and the neck mean weld neck, raised face mean the flat face is not flat face, is a raised face. And the gasket, when it comes with the like connection with the piping, it should be also raised face. Then it is said ASME Section VIII Division 1, then elliptical head with a 2-to-1 semi ellipsoidal head, and it is combination with 2-to-1. Then bolted cover. So if you see this, all these requirements are provided, and we are supposed to do all the mechanical calculation for all the portions and make fabrication drawings which can be used for by the fabrication yard or fabrication workshop to manufacture the vessel accordingly. Specification mean like all the guidelines with reference to let's say design point of view, loads point of view, load combination point of view. Like if a client would be looking for some additional feature over and above ASME VIII Division 1, those requirements could also be there, and like the manufacturer is used to follow the specification of the owner. Like a project specification point of view, if you see, this is a content of the case study, of the pressure vessel specification. If you see it says that general requirement, design life, tolerance and dimensions, then fireproofing and installation, worst case scenario and design margins, then design requirement point of view, which software could be used, design software, design conditions, design loading, design stresses, then accordingly, like if it's a material point of view, general specifications, bolting, gaskets, fabrication point of view, welding, weld repairs, post-weld heat treatment, then inspection and like testing and certification requirement as well. So if you see this, all these requirements are specified along with the data sheet and nozzle orientations. So then like a mechanical engineers are trying to design the pressure vessel. So calculation steps in like a PWHT software, set units, select design code. Like it's like how we do that. Enter design constraints as per the loading, temperature, pressure test, radiography. Enter wind code, wind data as per the site conditions. Enter seismic code and seismic data as per the site conditions, and provided in the data sheet and the specification. Like see, enter design constraint, for example, enter pressure vessel, design mean 160 psig and full vacuum from outside. Enter temperature, which is the design temperature of the vessel. Select test type and position, construction type, select degree of RT, whether it's a full or random or spot. Then calculate step, like step 4, enter wind data. There is basically, if you see ASC 95 and UBC 1997, and their conditions like what seismic zone, importance factor, seismic coefficient near source factor, and seismic zone 2A, and then force factor, and similarly for the wind side also, how it would be wind speed, vertical position, and so and so. Then next part is enter, like you can start generally from the bottom side of the same tower. See, this is a skirt, and then there would be a head connection point of view there. We'll go there, enter bottom skirt data and its base ring. Enter bottom dish and data, Enter data for the shell 1. Enter data for intermediate flange 1 and 2, which is here. You can see that. Then enter data for inter shell 2, shell 3, and shell 4. Enter intermediate flange 3 and 4. Enter data for top shell 5, if you see that this here. Then enter top flange and bolted cover data. Enter nozzle data. You see, if we keep entering as the vessel is made, and you can see on the side. So PWHT is quite easy to use, so it's not so difficult. Then skirt and base ring, for example, there is a node number 10 to 30 is the skirt, right? Cone skirt upper dia 610 mm and base dia 1285 mm is given by the client. Then enter material for skirt, which is SA240316L. Total skirt length is 2007 mm. Base plate material is also SA36. Then double base plate is there. You can see this here. Enter anchor bolt, which is 12 in quantity. Then enter gusset thickness 12 mm and width is 95 mm. The skirt base ring data normally is entered as we described before. Then you can see that how the data is being entered, base ring information, then bolting information, then set default value, whether analyze or design, we can do both. The material values, UNC type also is there, what kind of threads are there. And here the base ring type, whether this type, which type is applicable, we need to select that. Then bottom dish end is the when vessel start. First one is from node 30 to 40. Enter dish end type elliptical. Enter inside diameter, which is 610. Provide thickness, which is 6 mm, which is selected or nominal thickness first. Then select material of construction, which is SA240 type 316L. Enter internal, external pressure and temperature on that particular vessel. The values are given here. Shell course number 1. Enter inside diameter and length of the shell, which is 610, and length is 1960. Provide thickness with 16 mm. Select the material 240 same. Enter internal and external pressure and temperatures as applicable on all components. If we entered first on the lower bottom head, then it would be carried forward to other sides as well. So we have gone to head, and then we have put the basically first shell, and then there would be a flange. As per the configuration which is required by the client, we can make step by step. Course 1, then intermediate flange 1 and 2. A node 50 to 70 are the intermediate flanges. Flange height is 90 mm. Select material, then enter internal, external pressure and temperature, flange data, OD, ID, PCD, bolt size, and quantity. Gasket data is also filled in. This is the a field in the PWHT where we enter the data of the both flanges. So still data is there, and we have to see the flange type, and then accordingly all the data, ID, OD, PCD, type of material, threads, and so on is entered. We have if we try to fill in, then we will have an example or sample also available, and you can also get help from the seniors. So then it's not so difficult if we have the guideline available, senior available. Yes, without senior, without training, it would be risky to design the vessel yourself because you will make any mistake. So intermediate shell course 2, which is enter same diameter and length of the shell, then provide thickness same, select material, enter internal, external pressure and temperature, or carry forward from the previous node as well. So this is a course 3. Similarly, course 4, then intermediate flanges again 3 and 4, same way as we did earlier. Then also flange 1 and 2, shell course 4, same type of entry. No thickness has decreased. Like you see, the inside diameter and length of the shell is 2 is shell 2 ID 610. ID would remain same. Length is 1300 mm. Thickness has been decreased 8 mm, 16 mm to 8 mm. Select material, enter internal, external pressure and temperatures. Then we got top flange and bolted cover. Node 140 to 160 are the intermediate flanges. Flanges height is 100 mm. Selected material is same. Enter internal, external pressure and temperature. Then the same flange data is added. Gasket data is added. Then nozzles type with the pipe and flange. Enter pipe data. Enter flange data. Check weld strength and location also. This is the screen of the basically PWHT for the nozzles. Then calculation in the PWHT software. After completion, geometry input data, run analysis. You can also design or analysis. Two parts are there. So run analysis because you have provided all the input data. and then you can compare that whether it's passing the criteria or not. Then check output from the report. Use this output and generate general arrangement and fabrication drawing from the software. You can also do that. So here is the basically the complete vessel with all input data. You can also print out and you can verify. And this is a vessel design summary, like as we could, whatever data we input, you can see here. Then it is the what material construction we have used. Like if it is a normal size, material point of view, impact tested or not, the complete data, shell, head, flange, skirt, nozzles. So all are made and the base material. And then if you see the next slide, the thicknesses what are entered, 16 mm, 8 mm, 8 mm or the flanges. And then required thickness as per the code is very less, if you can see that. Then required thickness externally as per this, and longitudinal efficiency, circumferential efficiency, which are used as per the RT. So data is there. And then these are the stress values, like a distance to support, cumulative wind shear, earthquake shear, wind bending, and so on. Then these are required thicknesses, which is coming if you say 8 mm versus 2 mm, because bending movement is basically governing. Then here, cylindrical shell calculation also. Basically, elastic modulus or chart this, and you can check that load point of view. Shell external pressure calculation it is. So these are the nozzle, like a type of the nozzle what we prepared, like entered, insert, set in nozzle, no pad, no inside projection. This is what the design is. Then reinforcement calculation is done by the software itself, and thickness is verified. Then output nozzle thickness point of view. So parallel to the vessel wall, then parallel to vessel wall, normal to vessel wall thickness, no pad, and this is the thickness of data what is provided. Result. So it is like actual thickness is this, and versus this. So then the next is a skirt design point of view. Then summary of the baseline thickness calculations. So by all the checking, we have analyzed and we got the design, and then we got the drawing also, general arrangement drawing generated by the software. And then these are the more internal details which are provided. We can make ourselves also. And these are the basically fabrication detail of all the nozzles. So these are the fabrication drawing for the external basically ladders and other platforms and supports. So these support drawings are made by the mechanical engineers or the vessel design engineers with the details available. So pressure guidebook point of view, like if we say there is like a general handbook if you want to use, but there is a pressure vessel design manual by Dennis Moss or a pressure vessel handbook by Magessi. I used mostly Magessi, so it's quite easy to use. So like how the vessel is designed, I clarified to you, but you cannot practice it because time is less. So if you would do practice and you have access to PWHT or any other software, you can follow, or you can use Magessi's handbook, and you can do all these calculations by your hand also. So it concludes our discussion. We say take more questions if there are any, and then we'll be saying bye-bye for the day. Yes, Gail?
Okay, question there.
Yeah.
How the joining of plates or piping of different thickness addressed?
See, first of all, like when we make weld joints, whether it's the nozzle to shell, and whether like a flange to, a pipe to pipe, or one course to other course. So those mechanisms are available under ASME UG12, and the welding details available. So those guidelines are supposed to be followed.
Next question. Can you describe the difference between MAWP and design pressure?
MAWP is maximum allowable working pressure, and design pressure is based on the what pressure is identified by the process people or the owner. Sometimes the MAWP is more than design pressure, but MAWP should not be less than design pressure. If it would be less than design pressure, then pressure vessel will not be meeting the design criteria of the pressure vessel. So MAWP is considered should be always more than design pressure of the vessel, because the vessel, when you are trying to design, you're providing various thicknesses for various components, and you always try to provide some extra thickness so as the vessel should be able to sustain minimum design pressure which is specified. So it means the pressure vessel may have a capacity to sustain little extra pressure. That's why we call that maximum allowable working pressure.
Next question. Pressure vessels under vacuum.
Yeah.
Next.
See, like FW, if you see that this vessel is also designed under FW and shell external pressure. So this is calculation done for external pressure. So the pressure vessel is designed both for internal pressure as well as for the external pressure.
Next question. If there is any localized pitting corrosion, depth size 1.6 millimeters in cladded shell, 30 mm base metal and 3 mm SS cladding, and the pressure vessel is PWHT, so is it mandatory to repair the pitting or we can tolerate them?
See, today's subject is, this is not the today's subject, we are designing new vessel. Yes, this is the FFS case. If any vessel is cladded and if there's a pitting in the cladding, that can be repaired because the PWHT is applicable on the base metal, right? And if the PWHT is also applicable on the cladding material, then it would be a difficult aspect. So what my understanding is, PWHT is done on the base metal, not on the cladded vessel, because if you do PWHT after cladding, then due to the difference in coefficient of thermal expansion in the carbon steel and the cladding material SS316L or other, there could be a breakage of the material.
Next question. What about re-rating the pressure vessels?
See, re-rating the pressure vessel is like if the metal loss is there and if your vessel is lost some certain thickness or some certain defect is there, so and you are unable to repair that defect, then a re-rating is done to the lower pressure of that pressure vessel or equipment.
Next question. How to calculate requiring torque for bolts and studs during bolting of flanges for hydro tests?
See, there's a certain criteria what you use. It is not calculated, but you use certain torque to ensure that the flanges and the bolts are tight enough to prevent the leakage.
Next question. Why only longitudinal and circumferential stresses are considered in ASME 8?
See, both combinations are being used, but for the pressure containment, circumferential and longitudinal stresses are considered, but for loads like a wind and seismic or the bending loads, bending stresses, torsional stresses, other stresses are also considered. For pressure containment, only two, but other stresses are considered.
Next question. What are the recommended thickness for pressure vessels based operating temperature and design pressure? Let's say design code ASME Section VIII Division 1, refrigerant and ammonia.
See, if you remember that we have given the thickness was 2 mm, sorry, we can go to that particular slide, the minimum thickness one, 6 mm, if I can go to this. Forget the slide, this slide, 1.6 mm, then 5 mm or 6 mm, three thicknesses are given basically for the different scenarios. So I forget that my particular slide and it will be difficult for me to find that now. But for minimum required thickness are given for the different services. One for water and air, one for like unfired, 6 mm is the minimum thickness, I think, in the refrigeration side. Okay, good. Next question, because I'm able to find that.
Next question. Load during shifting and lifting is considered for designing the vessel?
Yes, when you're lifting, lugs are basically attached with a shell or any location of the pressure vessel. So those calculations are, those loads are also considered.
Next question. What are the major factors that we should consider when designing a pressure vessel?
See, there are UG22, all kind of loads, internal, external, process, wind, seismic, weather, all kind of loads are required to be considered.
Next question. What's the flange diameter criteria?
Flange diameter criteria is as per the applicable nozzle, right? If a nozzle is 2-inch, flange would be 2-inch. If the nozzle would be, let's say, 24-inch, then flange would be 24-inch.
Next question. Limitation only for diameter. How about the length?
See, a length is like when you are making a nozzle neck, so it goes with a standard length is also given, and sometimes you can increase a little bit based on the configuration of the nozzle to attach with a particular vessel. So I found that slide. If you can see that 1.5 mm for general service, 2.5 mm for steam, air, and water, 6 mm for unfired steam boiler. So it means your case could be, let's say, if we take 1.5 mm for general service, 2.5 mm for steam. So you have to see which criteria would be applicable on your case.
Next question. Do we need to remember these codes such as UG, UW, and UB?
No, we should know that these are the relevant sections and the time of use. We can go to those standards and we can open them.
Next question. For which vessel we need to perform PWHT? What is the criteria?
So see, liter service and the thickness is more than certain limit. Then you need to do PWHT and certain carbon contents also. So these requirements are specified in UCS requirement, and those can be followed.
Next question. What will happen if the addition revised, but the vessel is under construction and 80% completed?
No, there are many vessels who are designed as compared to the old codes. So they're kept in service, and we have not seen any vessel being put out of service due to new code. As per now, before 2000 and after 2000, required thicknesses are decreased, not increased as such. So code will not have any effect if the vessel is already fabricated or under fabrication and being installed.
Next question. When do we usually perform hydrostatic tests?
After completion of fabrication process, hydro test is done or pneumatic test is done. Or after a major repair or modification, hydro test is also required.
Next question. What does meant by MAWP in hot condition?
See, MAWP is same maximal working pressure. So whatever the condition is, because if the temperature is high, MAWP would be lower, because it cannot be as high as at the cold temperature.
Next question. What is the criteria of hydrotest pressure of existing vessels after modification? Say 10 years old.
So, see, modification means if there's any changes in the vessel, welding or PWHT, and there is a fear if there could be any flaw or any defect in the vessel which may create a problem post-operation. So it's a necessary to make sure a vessel is checked properly, and hydro testing is one of the checking process of the pressure vessel.
Next question. Can you please explain what is consideration on selecting PV head design? Ellipsoidal, hemispherical, or toruspherical?
See, these decisions are made by the process side, like what kind of head process engineer require for that particular pressure vessel.
Same question as before. Can you explain difference between ASME VIII Division 1 and 2?
So the safety factor difference only, ASME Division 1 got a safety factor of 3.5, and ASME VIII Division 2 is 2.4. And the first vessel can, ASME Division 1 works up to 15 psig to 3000 psig, and ASME VIII Division 2 is normally selected for 3000 to 10,000 psig pressure range.
Next question. What are the main crack types during pipe inspection as compared to vessel?
See, pressure vessel and piping both can have similar kind of problems, because the design code are also similar to each other. The type of material, manufacturing point of view, welding point of view, both are circular shapes, diameter only varies. One is if it's an ERW pipe and then plate welded vessel. So the nature of problem both in the piping and pressure vessel go side by side. And the only difference is seamless pipes would have a different problem, plate welded pipes would have different issues. And since all the vessels are mostly plate welded, so their issues can be compared with the ERW or larger dia pipe problems.
Next question. Please explain about SS to CS welding as well as SS to CS flange joint, for example, in joining, stelling welds.
See, I would acknowledge it, like, since I'm not a welding expert as such, so we take help from the welding experts if we have to, in the development of welding procedures for the various metals. And there's a criteria which should be followed. And the welding, experienced people are writing WPSs, because I am mostly from the design side. So we do not work on the writing of the WPS and the PQRs. Those are from the fabrication and the QA/QC department people. They are doing those jobs.
We can do one more question, sir.
Yes.
For in-service repairs modifications, can we use WPS and PQR used during construction?
See, during construction, WPS and PQR records can be used for the repair also, but for repair, there could be a different conditions. And in general, companies are having WPS and PQR done for the repair activities for various kind of materials, and those are used in case they need to do any repair or modification. Okay, sir, thank you very much for the day, and I hope this presentation was useful. I know that is a very basic, and it's only give you orientation. Like if you wish to do any design of a pressure vessel, it's not so complicated, and you can do easily, but you need certain supervision and somebody to guide you. And the designing of any pressure vessel, like we always say that there would be two levels, like one a doer, other checker. And checker should be at least experienced person and trained, so as we don't take any risk for the owner. Thank you very much for the day. If any question, you can write us back, and we look forward to meeting you for our next webinar next month. Thank you.